Okay, so in this circuit for figuring out total resistance, what you should have done here is just add up R1 plus R2 plus R3. You know, what would happen if we had a fourth resistor or a fifth component or sixth component? What would you do? Yeah, you would just continue to add them no matter how many there were throughout that whole series circuit. All right. So we have, if I were to do this, our RT, we have 220 ohms plus 470 ohms, and then we have 1.2k ohms. What do we know have to do about that 1.2k ohms? Yeah, exactly. I gotta convert it back, right? So I gotta move the decimal places 3 to the right, so I get 1200 ohms, which hopefully you did. So my total, if I add those together, I get correct 1890 ohms. That's my total resistance. Quick question, is that a lot of resistance? No, it's really not a lot of resistance. But again, you have to look at the circuit too. It could depend. If it's a really, really small circuit, like in your cell phone or something like that, that could be a good bit. But in your house, that's like nothing. It's not very much. Okay. All right, so if we're figuring out total current here, notice how I wrote the formula. This again is what? What is this? Somebody's law. This is Ohm's law, right? I rearranged it to solve in terms of current, total current. And notice when I'm looking at total current, I want to have total voltage and total resistance. So if I took my voltage and divided it by only the 220 ohm resistor, that would only give me the current that's going through that one section, which we're going to find out that in the end our current should be the same, right, throughout. But we have to figure out our total resistance. Okay, so IT, let's go over here a little bit, is equal to my total voltage, which is 12 volts, divided by my total resistance, which is 1890 ohms, and I get a total current of say what? 6.3 milliamps, right? Because if you said 6.3 amps, that would be a completely different answer. So 6.3 milliamps, if you didn't convert it, you probably had something like this then, 0.0063 amps, right? Milli is that thousandth of an amp, so we have to move the decimal place 1, 2, 3 in order to make it 6.3 milliamps. Again, what's the caution, the word of caution here? What do you have to worry about? If I convert to 6.3 milliamps, what do I have to worry about later? You have to convert it back, right? Because our base unit is the amps, okay? All right, so that all looks good. Now what we need to do here is we're going to take a look at the total voltage, okay? If my screen comes back. There we go. So first thing I'm going to do is do the voltage drop. So in order to solve for voltage, how do I rearrange my equation? What's the formula for it? Current times resistance, right? Since current's the same throughout, my current for voltage drop through 1, 2, and 3 is going to be that 0.0063 amps. So you can add that to all three of them right off the bat because you know it's the same. What's going to change is the amount of resistance. So through the first resistor, it's times 220. Through the second resistor, it's times 470. Through the third resistor, it's times 1200 ohms. All right, if we do the math here, we get 0.0063 times 220, gets us 1.386. That doesn't sound right. Is that right? Okay. 1.386. Oh yeah, that is right. My apologies. 0.0063 times 470, we get 2.961. And then 0.0063 times 1200, we get 7.56. Now, if I added the voltage drop through each component, what do you think this is going to add up to be? What do you know? It adds up, in this case, it adds up to be exactly 12. And what you're going to find out is in the circuit calculations that you'll do, because we're measuring them, we're not quite as super accurate. There's voltage, there's resistance in wires and different things that it'll be close. But for you to get exactly the same, it's rare for us. Okay, but you'll find out it'll be really close.